Welcome to Night Cosmos Sleep. Far beyond Earth, Titan holds a vast reserve of resources that could force humanity to see this distant world in an entirely new way. Methane, water ice, nitrogen, and carbon-based compounds exist there in enormous quantities. In theory, they could be transformed into fuel, oxygen, and construction materials for journeys deeper into the outer solar system. But a place rich in raw materials is not necessarily a refueling station. Methane cannot turn itself into thrust. Ice cannot become oxygen on its own. And no factory can operate in the cold darkness without energy, machinery, and the ability to perform repairs over many years. So the question guiding this journey is not simply what Titan contains. The more important question is whether humans could transform what Titan holds into something that can actually be used. Now, we will begin our journey toward that distant moon, slowly looking through the haze that conceals it and exploring the true distance between a natural reservoir of resources and a functioning refueling station at the edge of the solar system. Nearly 1.5 billion kilometers from the sun, there is a world where rain is falling. Rivers still flow, and lakes still fill and slowly recede, yet not a single drop of liquid on its surface is water. Beyond the window of our imaginary spacecraft, Saturn gradually emerges from the darkness. The enormous planet reflects only the faint sunlight that has traveled an immense distance through space. Bands of creamy yellow and muted gray clouds blend together, while the ring system appears as a series of thin, luminous lines suspended against the blackness. The spacecraft continues forward. Saturn grows larger, but the destination of this journey is not the planet itself. Near the edge of those glowing rings, an orange sphere moves quietly along its orbit. This is Titan. From this distance, Titan reveals no mountains, valleys, or coastlines. There are no clearly visible craters like those on the Moon, and no contrasting bright and dark regions like those on Mars. The entire world seems wrapped in a thick yellow-orange haze, like a dim lamp glowing behind a pane of dusty glass. Titan is Saturn's largest moon, and the second largest natural satellite in the entire solar system. Only Jupiter's Ganymede is slightly larger. Titan has a radius of about 2,575 kilometers. It is larger than Earth's moon, and in terms of diameter alone, Titan is even larger than Mercury. But size is not what makes Titan most remarkable. Its true strangeness lies in the dense atmosphere that conceals it. Among all known moons, Titan is one of the very few worlds with an atmosphere thick enough to create clouds, winds, rain, and long-lasting weather cycles. Here, the sun appears as only a small point of light, far softer than it does from Earth. Titan lies about 9.5 astronomical units from the Sunday. An astronomical unit is simply the average distance between Earth and the Sunday. Because Titan is so much farther away, the sunlight there is nearly 100 times weaker than the light we receive on Earth. A beam of sunlight takes only about 8 minutes to reach our planet, but nearly 80 minutes to travel to the region of Saturn. When it reaches Titan's haze, that light is scattered into a muted orange glow that spreads across the sky. Even so, Titan is not completely dark. Daytime still exists there, though it is unlike daylight on Earth. Sunlight must pass through many layers of atmosphere filled with tiny particles of organic haze. As a result, the surface may be covered in soft, diffuse light, resembling late afternoon on a heavily misted day. Titan orbits Saturn once every 16 Earth days. In almost exactly the same amount of time, it also completes one rotation on its axis. These synchronized motions cause Titan to keep nearly the same side facing Saturn at all times. This phenomenon is known as tidal locking, similar to the way our moon always shows Earth almost the same hemisphere. A single day on Titan lasts nearly half a month by our measure. Light arrives slowly, darkness settles slowly, and each season can continue for many years. If it were possible to see through the haze from the surface, Saturn would appear almost motionless in one region of the sky. Yet, for most of the history of observation, humanity had no clear idea what lay beneath that haze. Telescopes could see only an opaque sphere. Visible light could not penetrate the thick atmosphere well enough to reveal the terrain below. Mountains, plains, riverbeds, and coastlines, if they existed, remained completely hidden. Titan was like a sealed room. its entire surface resting silently behind an orange curtain. Astronomers knew that Titan had an atmosphere, and they detected methane within it. But knowing that a world contains methane is not the same as knowing what that methane is doing. It might remain in the air, condense into clouds, or, under sufficiently cold conditions, fall to the ground and collect in bodies of liquid. The answer only began to emerge when humanity found ways to see through the veil. Beneath the haze lies a landscape that is both alien and surprisingly familiar. There are valleys shaped like drainage systems on Earth. Long channels curve across the terrain, small lakes are scattered near the poles, and vast seas have complex coastlines. Elsewhere, bands of dunes stretch for hundreds of kilometers, arranged in parallel like immense deserts. These features make Titan resemble a dim, shadowed version of Earth, but the similarity exists only in their shapes. The materials that form them are entirely different. On Earth, water evaporates from the oceans, condenses into clouds, and falls back to the surface. It runs down mountain slopes, gathers into streams, rivers, and lakes, and eventually returns to the sea. This cycle has shaped much of the familiar landscape around us. Titan has a similar cycle, but the liquid taking part in it is not water. The surface temperature is so low that water remains almost entirely frozen. This is not merely a thin layer of ice that can melt beneath sunlight. On Titan, water can be as hard and durable as bedrock. The rounded stones scattered across its surface may not be made of minerals like the pebbles found beside rivers on Earth. Many of them may be blocks of water ice, worn smooth over time. While water becomes stone, methane takes on the role of a substance that can shift between gas and liquid. Methane exists in the atmosphere, forms clouds, falls as rain, and then flows across the surface. Ethane and other hydrocarbons may also mix into the lakes and seas, creating dark liquid blends beneath the haze. When rain falls on Titan, bitterly cold droplets of methane strike the ice and organic material below. They may gather into temporary streams, thread through narrow channels, descend toward lower ground, and finally empty into lakes. After a heavy storm, a dry riverbed may suddenly fill. A depression may become a lake, then slowly drain as the liquid seeps into the ground or evaporates back into the atmosphere. Near the poles, lakes, and seas may hold enormous quantities of methane and ethane. Their shorelines contain bays, narrow straits, and peninsulas. Some may change with the seasons. Liquid levels rise and fall, while clouds form, drift across the sky, and disappear. Far from the polar seas lie immense fields of dunes around the equatorial regions. They are not composed mainly of rocky sand like the deserts of Earth. Many models suggest that their material contains organic particles formed in the atmosphere, which have fallen over long periods of time and been gathered by the wind into dark, long, evenly spaced ridges. These dunes, river channels, and methane seas show that Titan is not a motionless sphere. Its surface is still changing. Winds carry material from one place to another. Rain carves the terrain. Liquids move through valleys. The atmosphere exchanges methane with the lakes and the ground. Titan remains a world of weather and landscapes in motion. This brings us to the first paradox of our journey. Titan possesses many of the features we usually associate with a living, active world. There are clouds in the sky, rain falling to the ground, rivers crossing the surface, lakes, seas, shorelines, and changing seasons. Yet if a person stood there without protection, everything familiar would immediately become dangerous. The air could not be breathed. The cold would exceed anything found in a natural winter on Earth. Water would not flow in rivers, but would remain locked inside a rigid crust. The liquid around their feet would be methane and ethane at extremely low temperatures. This contrast can easily mislead us. By looking only at the shapes of rivers and seas, we might imagine that we are observing another Earth. But when the materials, temperatures, and light are different, the meaning of the entire landscape changes with them. The imaginary spacecraft begins to adjust its course. Titan is no longer a small sphere beside Saturn, it is growing larger beyond the window. The orange haze gradually fills more of the view, while the rings behind it become thinner and more distant. The instruments turn toward the surface, but visible light still cannot reveal what lies beneath. Only an opaque orange expanse stretches from one horizon to the other. Somewhere below that atmosphere, Rain may have just passed across a dark plain. A stream may be carrying methane toward lower ground. The surface of a lake may be perfectly still beneath a sky that is not blue. The spacecraft continues to descend. The haze thickens, slowly hiding Saturn from view. Somewhere beneath that orange curtain lie seas of liquid that a rocket engine might recognize as raw material. But between a methane sea and a usable fuel tank, there remains an enormous distance. For decades, Titan was little more than a faceless orange sphere. Humanity knew it existed, knew it was large and wrapped in a dense atmosphere. But every true feature of that world remained hidden behind a veil that ordinary light could not penetrate. Our imaginary spacecraft continues to descend. Saturn has disappeared behind the haze. Outside the window, the vast glowing rings are gone, replaced by a murky orange expanse stretching in every direction. Sunlight scatters through countless tiny organic particles until the sky has no clear horizon. Titan seems to have neither ground below nor open space above. The spacecraft is entering a world concealed within its own atmosphere. To lift that veil, humanity once had to undertake one of the longest and most complex journeys of the space exploration era. The Cassini spacecraft left Earth in 1997, carrying a smaller probe named Huygens. Together, the two spacecraft traveled through space for nearly 7 years, using the gravity of planets to gradually gain speed and change direction. They passed Venus, returned near Earth, continued past Jupiter, and only then entered the vast darkness surrounding Saturn. When Cassini reached the Saturn system in 2004, its mission involved far more than observing the ringed planet. It would also fly past many moons, measure magnetic fields, photograph the rings, and, most importantly, find a way to see through Titan's haze. Huygens had a different purpose. It was not designed to orbit Titan. It was built to fall. Near the end of 2004, Huygens separated from Cassini and began drifting through space alone. With no large engine to adjust its course, the small probe followed a trajectory calculated in advance. For days, it moved quietly toward the orange sphere. Then, in January 2005, Huygens entered Titan's upper atmosphere and began a descent unlike anything any previous spacecraft had attempted. At first, Huygens plunged into the atmosphere at tremendous speed. The heat shield at its front endured intense heating as Titan's air compressed around the spacecraft. This created a strange contrast. The surrounding atmosphere was colder than any natural environment on Earth, yet during those first few minutes, the probe's rapid motion exposed the shield to extreme heat. Once the spacecraft had slowed enough, a small parachute deployed to pull away the rear cover. The main parachute then opened, slowing Huygens further and suspending it within the dense atmosphere. The front heat shield was released, exposing the cameras and instruments waiting to observe Titan. Even then, the orange veil had not fully opened. Huygens was descending through thick layers of organic haze where light scattered in every direction. These particles form when ultraviolet light and energetic particles act upon methane and nitrogen in the upper atmosphere. Molecules are broken apart, recombine, and produce increasingly complex compounds. Over time, they gather into tiny particles that drift downward, giving Titan its distinctive yellow-orange color. Huygens passed directly through this material. Its instruments recorded temperature, pressure, atmospheric composition, and wind speed at different altitudes. The probe did not descend vertically. Winds pushed it sideways, sometimes causing it to rotate and sway beneath the parachute. Scientists on Earth could not control each movement in real time. A signal needed more than an hour to cross the distance between Titan and our planet. Huygens had to complete the entire descent on its own, following commands prepared long before. As it moved deeper, the haze gradually began to thin. The light remained weak, but for the first time, the cameras started to detect bright and dark regions that did not belong to the atmosphere. Titan's surface was coming into view. In the first images, long, dark lines crossed a brighter region of terrain. They branched apart, joined together, and flowed toward lower ground. Their shapes closely resembled a river system seen from above. Small channels fed into larger ones, valleys appeared to have been eroded by liquid, and low-lying regions suggested the presence of shorelines. This was one of the most important moments in the history of Titan's exploration. The opaque sphere that had once shown no terrain suddenly became a world with recognizable structures. The dark lines did not prove that liquid was flowing at the exact moment Huygens passed overhead, but their shapes revealed that the surface had been shaped by flowing liquid in the past. Rain had fallen here. Liquid had gathered, moved downhill, and carved channels across the landscape. Huygens continued to drift through the atmosphere under the influence of the wind. As it descended farther, its cameras revealed regions resembling plains, drainage channels, and a darker surface near the landing site. The main parachute was replaced by a smaller one so the probe could descend more quickly, preventing it from spending too much time drifting through the atmosphere before its batteries ran out. After more than 2 hours of descent, Huygens touched the ground. The landing did not resemble a spacecraft striking bare rock. The data suggested that the surface may have given way slightly before stopping the probe, like a layer of soft or damp material resting above firmer ground. Huygens tilted to one side, but continued operating. Its cameras transmitted the first images ever taken from the surface of Titan. Before the probe lay a dark plain scattered with rounded objects of different sizes. They looked like pebbles resting in a dry riverbed. Many had smooth surfaces and rounded shapes, suggesting that they had once been transported or worn down by liquid. But these rocks may not have been rocks in the way we usually understand them. Titan's surface temperature is about -179 degrees Celsius. At such temperatures, water cannot exist as ordinary flowing rivers. It freezes so solidly that it can form the ground, cliffs, and rounded stones. On Titan, water ice can play the same role that silicate rock plays on Earth. Methane exists under very different conditions. It can remain as a gas in the atmosphere, condense into clouds, fall as rain, and gather as liquid on the surface. In Titan's landscape, the roles of water and methane are therefore almost reversed. Water forms the solid structure of the terrain, while methane moves between the sky and the ground. Huygens operated on the surface for only a short time, but its images and measurements changed the way humanity saw Titan. For the first time, we knew what the light beneath the haze looked like. For the first time, a spacecraft had touched the ground of a world in the region of Saturn. And for the first time, river-like channels and rounded stones of water ice appeared not only in models, but in real data. While Huygens made its single journey to the surface, Cassini continued orbiting Saturn and returned to Titan again and again. From above, the spacecraft faced the same old problem. Visible light still struggled to pass through the haze. But Cassini carried radar, an instrument that did not need to see the surface the way human eyes do. Radar transmitted radio pulses toward Titan and measured the signals reflected back. Different surfaces responded in different ways. Rough terrain could produce a strong reflection, while flat, calm liquids often absorbed most of the signal, causing them to appear extremely dark on radar maps. With each flyby, Cassini assembled scattered pieces of the map. Titan began to emerge, not as a single-colored sphere, but as a world divided into dramatically different kinds of terrain. Near the polar regions, radar revealed clusters of small lakes. Some had rounded shorelines, others stretched along valleys, and some appeared to be dry or filled only during certain seasons. Between them lay elevated regions, drainage channels, and landscapes that may have been eroded by liquid. Then, even larger dark regions appeared. These were not merely lakes, but bodies of liquid vast enough to be called seas. Kraken Mare is the largest known sea on Titan. It stretches across the northern polar region, with a complex shoreline shaped by numerous bays and narrow straits connecting different sections. Nearby lies Ligeia Mare, smaller but still immense, with a radar surface that appears exceptionally dark and relatively smooth. Data from Cassini indicate that these seas contain mainly methane and ethane, along with several other dissolved compounds. These measurements do not turn Titan into a replica of Earth. Its dark seas are not filled with salt water. There are no blue waves beneath a clear sky. The liquids are so cold that any material, machine, or human body brought from Earth would require extreme protection. Yet the shapes of the shorelines, the drainage channels, and the distribution of the lakes still reveal that Titan has a true climate system. Methane evaporates from the lakes and seas. It enters the atmosphere and, when conditions are right, can condense into clouds. Those clouds move with the winds, and methane eventually returns to the surface as rain. The liquid flows through rivers, valleys, and low-lying regions before collecting in lakes or seas. Some of it then evaporates again, beginning the cycle anew. This cycle resembles Earth's water cycle, but the two worlds do not operate in exactly the same way. The amount of methane in Titan's atmosphere changes with the seasons and may be replenished by sources that are not yet fully understood. Rainfall may be rare in some regions, but intense when it occurs. A river can remain dry for a long time and then suddenly fill. Lakes may expand, shrink, or leave empty basins behind as climate conditions change. Beyond the lakes and seas, Cassini's radar also revealed enormous dune fields around the equator. They stretch for hundreds of kilometers, run almost parallel to one another, and cover a large portion of Titan's surface. The particles forming these dunes may be organic material that fell from the atmosphere, was altered on the ground, and then carried by the wind. Titan therefore has two systems shaping its surface at the same time. Liquids form rivers, lakes, and coastlines. Winds build long dunes across the drier regions. Both operate within an environment of extreme cold, where water becomes rock and hydrocarbons can become weather. But the surface is not the whole story. Measurements of Titan's rotation, gravity field, and deformation suggest that a liquid water ocean may exist deep beneath its icy crust. This ocean is not Krakenmeer or Ligeameer. The visible seas lie on the surface beneath the atmosphere and contain hydrocarbons. The subsurface ocean, if current models are correct, lies far below, buried beneath a thick shell of water ice. No spacecraft has ever drilled down to it. No one knows its exact depth, composition, or conditions. It may contain water mixed with other substances that help keep it liquid at low temperatures. But until more direct measurements become available, the underground ocean remains a conclusion built from multiple lines of indirect evidence, not a body of water that has actually been seen. Our imaginary spacecraft has now passed through the thickest part of the haze. Data from Huygens appear alongside Cassini's radar maps. Dark river channels, organic dunes, and polar coastlines come together to form a more complete picture of this world. The radar instrument turns toward a dark sea. A radio signal leaves the antenna, passes through the atmosphere, and nearly disappears when it reaches the smooth surface below. Within that darkness may lie trillions of tons of methane and ethane. But an enormous reservoir has value only when humanity knows exactly what it contains. The dark sea still lies beneath our imaginary spacecraft, so smooth that it nearly swallows the radar signal whole. There is no blue reflection, no white foam on the waves, and no bright horizon. There is only a black surface of liquid resting beneath the orange atmosphere, as though Titan were keeping part of its secret hidden within its deepest basins. At first glance, a sea of methane may suggest a very simple idea. Methane is a fuel. Rockets can burn methane, and Titan has methane in its atmosphere, its clouds, its rain, and its vast lakes and seas. So perhaps all that is needed is to lower a pipe, pump the liquid upward, and feed it into an engine. But nature rarely arranges matter according to the exact standards human machines require. Most of Titan's atmosphere is nitrogen, making up about 95%. Methane accounts for a smaller share, usually a few percent, though the amount can vary with altitude, season, and location. Mixed among these two main components are small quantities of other gases and carbon-bearing compounds. This atmosphere is far denser than what a moon would normally possess. The pressure at Titan's surface is about 60% greater than the average pressure at sea level on Earth. A spacecraft descending here does not stand in a vacuum as it would on the moon. It rests beneath a thick column of gas. Where winds can push parachutes, clouds can move across the sky, and methane can fall as rain. Nitrogen gives Titan's atmosphere a certain familiarity, because Earth's air is also composed mostly of nitrogen. But Titan has almost no free oxygen for humans to breathe or for an ordinary flame to sustain itself. Methane exists in a cold environment lacking oxidizers, allowing it to accumulate in ways very different from those on our planet. High in the atmosphere, ultraviolet light from the sun and energetic particles within Saturn's environment collide with methane and nitrogen, breaking chemical bonds and leaving behind smaller molecular fragments. These fragments meet, recombine, and form new molecules. Some are broken apart again. Others become more complex, heavier, and less able to remain suspended as gases. Through many stages of chemical reactions, the atmosphere produces a broad mixture of compounds containing carbon, hydrogen, and nitrogen. Some gather into extremely small particles of organic haze. These particles scatter light, hide the surface, and give Titan its characteristic orange color. They drift through the atmosphere and slowly settle downward, covering the plains, mixing into the soil, clinging to pieces of water ice, and becoming part of the dark dunes around the equator. The orange haze, then, is more than a curtain concealing the landscape. It is also the visible trace of a natural chemical factory that has been operating in Titan's atmosphere for a very long time. Methane is the most obvious starting material for this factory. Some remains as gas, some condenses into clouds and rain, some collects in lakes and seas. Ethane is also present within these bodies of liquid, along with other compounds that may dissolve into the mixture or settle to the bottom. In drier regions, especially near the equator, carbon is stored within dunes of organic material. The exact composition of these particles has not yet been fully measured directly. Models and spectral data suggest that they may contain heavier organic molecules formed in the atmosphere and then altered further on the surface. In addition to methane and ethane, observations have detected or suggested the presence of propane, ethylene, acetylene, and many other carbon compounds. There is no need to remember every name to understand their importance. What matters is that Titan does not contain only one kind of hydrocarbon. It holds an entire family of materials that industries on Earth often treat as chemical feedstocks. On Earth, carbon and hydrogen are processed in many ways to create fuels, plastics, solvents, synthetic rubber, and insulating materials. Some molecules on Titan might be separated, purified, and transformed into polyethylene, flexible materials, protective coatings, or feedstock for three-dimensional printing systems. A research preprint, published in 2026, examined Titan from this perspective. Rather than treating methane and organic compounds only as subjects of scientific study, it asked whether they might become local sources of raw material for long-term operations in the outer solar system. It is an appealing idea, but a clear distinction must still be maintained between chemical possibility and engineering practicality. A molecule that appears suitable on paper does not automatically become a usable product. It must be found in sufficiently high concentrations, collected by machinery capable of surviving the cold, separated from other substances, processed through controlled reactions, and tested for purity. Our imaginary spacecraft lowers a sampling device toward the dark sea. A narrow tube touches the surface, draws up a small amount of liquid, and transfers it into an analysis chamber. At Titan's temperature, the sample remains liquid, but it does not necessarily contain methane alone. A natural lake may contain methane, ethane, dissolved nitrogen, and many other compounds in proportions that vary with location, depth, temperature, and season. Liquid near the shore may differ from liquid farther out at sea. Material falling from the atmosphere may partly dissolve. Heavier compounds may collect on the bottom or along the shoreline as methane evaporates. A rocket engine's fuel tank is an entirely different environment. Its contents must be precisely known. Temperature and pressure must remain within design limits. Impurities must not clog pipes, leave deposits on valves, or make combustion unstable. The tank material must withstand extreme cold without becoming brittle, while pumps must deliver fuel at exactly the required rate after years spent far from any repair facility. This difference can be understood through a familiar comparison. An oil field is not a gas station. Crude oil beneath the ground is not pumped directly into a car engine. Between the two lie extraction wells, pipelines, refineries, storage tanks, testing laboratories, and a distribution network. A similar distance separates Titan's methane seas from a rocket fuel tank. The difference is that this entire industrial system would have to operate at -179 degrees Celsius beneath a sky far from Earth, on a world where no human has ever repaired a machine in person. Even collecting methane from the atmosphere would not be simple. Methane makes up only a small portion of the air. so equipment would need to process enormous volumes of gas, separate the methane from nitrogen and other components, and then compress or cool it into a suitable state. Drawing liquid directly from a lake could eliminate some steps, but it would require pipes or robots capable of operating in cryogenic hydrocarbons whose composition has not yet been fully examined on site. The organic dunes present a different challenge. They may contain a rich source of carbon, but they are not a uniform reservoir of liquid. The material would have to be excavated, transported, cleaned, and separated into useful components. Some processes might require high temperatures, high pressures, or catalysts brought from elsewhere. Titan is therefore not a single storage tank. It is more like an unclassified region of natural raw materials. The atmosphere provides one mixture. The seas provide another. The dunes hold heavier molecules. Each source would require its own kind of machinery and its own processing chain. But even if humans purified the methane and placed it inside a perfect storage tank, the engine still could not operate. Methane is a fuel, but fuel is only one part of combustion. To release energy, methane must react with an oxidizer. On Earth, a flame usually draws oxygen directly from the surrounding air. A rocket engine cannot depend on the outside atmosphere, so it must carry both fuel and oxidizer in separate tanks. Titan's atmosphere contains almost no free oxygen. This explains why seas of methane can exist beneath a dense sky without bursting into flame. Titan holds vast quantities of material that a fire could consume, but it lacks the component that would allow that reaction to begin and continue. Titan is not a world waiting to catch fire. It is a world where natural fuel and natural oxidizer are kept far apart. That changes the meaning of Titan's hydrocarbon seas. They are still valuable. Methane could become fuel, a source of carbon, or a chemical feedstock. Ethane and other compounds could support many manufacturing processes, but none of them removes the need to build processing systems, supply energy, and secure a reliable source of oxygen. Inside the analysis chamber, the liquid sample is gradually purified. Dissolved nitrogen is separated out. The methane is transferred into a small tank, where sensors confirm its temperature, pressure, and purity. On the display, every reading falls within the limits of the model. A pipeline carries the sample toward the test engine. A valve opens. Methane enters the combustion chamber, but the engine remains silent. No flame appears because Titan has provided only one half of the process. The other half is not found in the atmosphere or floating on the dark seas. It is locked inside the hard water ice beneath the surface, where oxygen exists but cannot escape freely. Titan may provide one half of the flame. The other remains trapped in the icy rock below. The test engine remains silent. The methane has been purified, carried through the pipeline, and is waiting inside the combustion chamber, but no flame appears. On the display of our imaginary spacecraft, one half of the equation is ready. The other lies beneath Titan's dark ground, held tightly within a substance that seems very familiar: water. But on Titan, water does not flow in streams, collect in puddles, or cover the ground as soft snow. At a temperature of about -179 degrees Celsius, it freezes so solidly that it behaves much like bedrock. The rounded stones once seen by Huygens may be pieces of water ice worn smooth by flowing methane. Raised terrain, low cliffs, and much of Titan's outer crust are also believed to contain enormous quantities of water in solid form. This makes Titan a world with two reservoirs of material separated from one another. On the surface and in the atmosphere are methane, ethane, and many carbon-bearing compounds. Within the icy crust is water, where hydrogen and oxygen remain bound together inside each molecule. If those two elements could be separated, the oxygen could help methane burn, while the hydrogen could become another source of useful material. But before oxygen can be produced, humans must accomplish something that sounds simple in words and is extremely difficult in practice: extracting water from rock. Our imaginary spacecraft lowers a drilling system onto a plain not far from the shoreline. The surface is not entirely clean. Over long periods of time, organic particles have fallen from the atmosphere and mixed with fragments of water ice, forming a layer of dark soil. Some areas may be covered by softer material, but beneath it lies a cold, solid foundation of ice. The drill begins to turn. In Titan's environment, metal contracts in the cold, ordinary lubricants may freeze, and moving components must be kept warm enough to avoid becoming stuck. The equipment must not only be powerful enough to cut through the ice, it must also prevent heat from its own motor from melting the surrounding material unintentionally, allowing the water to refreeze around the drill and lock it in place. Small pieces of ice are carried upward through a sealed tube. They are not transparent like ice cubes taken from a freezer. The ice may be mixed with organic material, dust, salts, or other compounds. Its true composition would vary from one location to another, and no deep drilling campaign has yet been conducted on Titan to reveal how pure the near-surface ice might be. These pieces of material are transferred into an insulated chamber. The door closes, separating them from the methane and nitrogen atmosphere outside. Only then does the process of turning rock into water truly begin. On Earth, melting a block of ice usually requires little more than moving it into a warmer place. On Titan, that ice begins at a temperature nearly 200 degrees below water's freezing point. The system must supply heat for a long time, first raising the temperature of the ice, and only then carrying it across the boundary where solid becomes liquid. The energy is not needed only to melt the ice. It must also keep pipes, valves, and processing tanks from freezing again. A single section of pipeline losing heat too quickly could turn the water into a solid plug of ice and bring the entire system to a halt. Inside the processing chamber, the ice slowly begins to soften. A thin layer of water appears around the heating element, then gradually spreads outward. This first liquid water cannot be sent directly into the electrolysis system. It must pass through filters that remove solid particles, organic material, and impurities that could collect on the surfaces of the electrodes. This is a step that can easily be overlooked when imagining resource extraction beyond Earth. A natural source of water is rarely as pure as machinery requires. If impurities accumulate, efficiency declines. If certain compounds react with the system's materials, pipes may corrode. If water freezes inside the filters, the entire processing line must stop so it can be warmed and cleaned. Once filtered, the water enters the electrolysis chamber. There is no flame here. There are only conductive surfaces, electrical lines, and a carefully controlled current. The electric current acts like an invisible wedge, driving the chemistry in a direction that forces the bonded components apart. Hydrogen is collected on one side. Oxygen appears on the other. This reaction does not create new matter. The hydrogen and oxygen were already present within the water ice. Electrolysis simply uses energy to release them from the bonds that kept them stable. The oxygen produced could be directed into life support systems. In a future base, humans would need oxygen to breathe, but they could not simply open a door and draw it from Titan's atmosphere. The air outside is composed mainly of nitrogen and methane. Oxygen would therefore have to be produced, stored, and circulated within sealed spaces. Another portion of the oxygen could be used in methane-burning engines. When fuel and oxidizer meet under the right conditions, energy is released as heat and a high-speed flow of gas. This is the flame that the engine at the end of the previous chapter was missing. Oxygen could also be used in fuel cells, where chemical reactions are carefully controlled to produce electricity rather than a large flame. It could support welding, cutting, and material processing. In some chemical production systems, oxygen would become a necessary reactant for transforming raw carbon resources into more useful products. The hydrogen separated at the same time is not a waste product. It could be used in fuel cells, take part in chemical reactions, or combine with carbon in recycling processes. Within a closed-loop life support system, hydrogen could help convert carbon dioxide into water and other compounds, reducing the amount of material that must be transported from Earth. These principles are not unfamiliar. Spacecraft and space stations already use systems for recycling water, controlling the atmosphere, and performing electrolysis. But operating them on Titan would be an entirely different challenge. In orbit near Earth, a failed system can receive replacement parts within a relatively short time. On Titan, every supply mission would have to cross more than 1 billion kilometers and take years to arrive. A small valve becoming stuck, a sensor drifting out of calibration, or a layer of material building up on an electrode could turn into a lasting problem if robots were unable to repair it on their own. After electrolysis, the hydrogen and oxygen would still not be ready for use. They would need to be completely separated from any remaining water, tested for purity, and then transferred into storage systems. The gases could be compressed to reduce their volume or cooled further until they became liquids, depending on the needs of the engines and the base. Each choice comes with its own difficulties. Compressed gases place enormous pressure on storage tanks. Cryogenic liquids require effective insulation and continuous thermal control. Pure oxygen can make many materials more flammable. Hydrogen is extremely light, can leak through tiny openings, and may weaken certain metals over time. Storage tanks, then, are not simply empty containers. They require valves, insulation, pressure sensors, and protective mechanisms. Titan's cold environment may help keep certain substances at low temperatures, but the thermal difference between the processing area and the outside world would still place stress on the materials. In the spacecraft's model, oxygen begins to collect inside a small tank. Another pipeline carries the purified methane from the previous chapter toward the combustion chamber. For the first time, both halves of the flame are present within the same system. But before the valves open, the energy display reveals something even more important. The drill has consumed electricity to cut through the ice. The heater has been operating for hours. Pumps have kept the water moving. Filters and electrodes require a stable power supply. Compressors continue drawing energy as they force the gases into storage. Methane and water ice may already exist on Titan, but transforming them into propellant is not free. Every kilogram of oxygen carries an energy history behind it. The energy required to extract, heat, purify, separate, compress, and preserve it. This creates the most important limitation of the entire idea. If a base must consume too much energy to produce propellant, Titan's abundance of methane no longer represents a simple advantage. The factory would only be worthwhile if its energy supply were stable, powerful, and capable of operating over long periods of time. Titan does not lack fuel. Titan lacks a factory powerful enough to awaken that fuel from its frozen state. That statement applies to more than methane. It describes the entire chain of materials lying dormant in nature. Water ice does not turn itself into oxygen. The atmosphere does not separate methane from nitrogen on its own. The lakes do not remove ethane and impurities by themselves. To transform a world into a source of supplies, humanity would have to build an entire system between the raw resource and the finished product. That system would also need to preserve heat that might otherwise be treated as waste. Heat from reactors, compressors, engines, and electronic equipment could be redirected toward the ice melting area. Warm water, leaving the electrolysis system, could transfer heat to the next batch of ice. Modules could be wrapped in multiple layers of insulation to reduce losses to the surrounding environment. On Titan, heat would not merely be a byproduct. It would be a resource that must be carefully recovered. Every unit of heat escaping through the walls of a module would disappear into a world always ready to pull everything back toward minus 179 degrees Celsius. Inside the processing chamber, the first droplet of water separates from the block of ice and falls to the bottom of the tank. It is almost insignificant compared with the vast methane seas outside. Yet to create that single drop, the drill, heater, pumps, sensors, and electrical system have had to operate continuously for many hours. The droplet touches the metal surface and trembles slightly in the low gravity. Behind the glass, it is more than water. It is oxygen not yet separated, hydrogen not yet collected, and a flame still waiting for the power required to keep the entire system running. On Titan, the most valuable resource may not be methane or oxygen. It may be energy. The first droplet of water still rests at the bottom of the processing chamber. Beyond the thick glass, Titan's darkness covers everything, while heat pipes slowly carry warmth through a small system newly assembled on the frozen plain. There are no cities here, no brightly illuminated towers or thousands of people moving beneath a dome. There are only a few low modules, several robots, storage tanks spaced across the dark ground, and the steady hum of pumps echoing through metal. If Titan ever becomes a place where fuel and materials are produced, Its first facility will probably not resemble a vast settlement. It may begin as a small automated system delivered from Earth, assembled piece by piece, and operated for many years before any human ever sets foot there. Each component must perform a clearly defined task. There is too little space inside the modules for unnecessary production lines. Energy is too precious to be used carelessly. Every machine must extract resources while also protecting itself from temperatures of -179 degrees Celsius. The imaginary facility is divided into 4 areas. They are separated far enough to prevent a single accident from spreading through the entire system, yet close enough to share electricity, heat, and pipelines. Robots move slowly between them, leaving wheel tracks across the dark organic material. The first area collects gases from the atmosphere. A large intake faces the gentle wind. Titan's air enters the system, carrying mostly nitrogen, a smaller amount of methane, and traces of many other compounds. The pumps do not have to work against a vacuum, because Titan's surface atmosphere is relatively dense. But the cold makes every mechanical movement more difficult. The air passes through filters that capture particles of organic haze. These tiny particles can settle on fan blades, pipelines, and sensor surfaces. Without regular cleaning, they form a thin coating that reduces efficiency and obscures optical instruments. The gas mixture then enters a series of separation chambers. Methane can be isolated from nitrogen by changing the temperature or pressure, or by using materials that hold one kind of molecule more effectively than another. Titan's naturally low temperature could assist with part of the cooling process. A system on Earth would consume a great deal of energy to bring matter down to such temperatures, while Titan already provides a cryogenic environment. But that cold is not an entirely free gift. Pumps still require electricity. Valves must still open and close precisely. Seals must remain airtight. If one section of pipeline becomes colder than intended, certain components may condense or freeze in the wrong place, creating a blockage inside. The atmospheric collection area therefore does more than cool material. In some places, it must also provide heat. One pipeline may be kept cold so methane can condense, while the section beside it must remain warmer so nitrogen can continue flowing. The entire system becomes a carefully maintained balance between preserving the cold and preventing unwanted freezing. Once separated, the methane enters an intermediate storage tank. It is not yet finished fuel. Sensors must still determine its composition, detect impurities, and confirm that the flow of collected gas remains stable. If methane concentrations in the atmosphere change with the seasons or weather, the production rate will change as well. Not far away is the ice extraction area. A drilling robot stands on broad supports to keep it from sinking into the surface layer. Its drill passes through the organic soil and reaches the hard foundation of water ice below. Titan contains enormous amounts of water, but the most accessible ice may not form a clean, uniform layer. It could be mixed with dark particles, salts, or materials that the machinery has never encountered under real operating conditions. The drill turns slowly. If it spins too quickly, friction produces heat and melts part of the ice. The newly melted water could flow into narrow gaps and immediately freeze again, trapping the equipment. If it turns too slowly, the extraction rate will not provide enough material for the electrolysis system. The drill's metal also contracts in the cold. Components fitted tightly together on Earth may change dimensions after reaching Titan. A narrow gap may become too wide. Two surfaces that once moved smoothly may press tightly against each other. Ordinary lubricants may thicken or freeze, forcing the machine to use specialized materials or keep critical components inside a heated enclosure. With every drilling cycle, organic material collects on the cutting surface. The robot must clean itself, using vibration, heat, or a separate tool. There is no technician standing nearby to remove the drill bit and wipe away each layer of residue. If the system cannot solve the problem on its own, it may remain inactive for years before another mission arrives. Once extracted, the blocks of ice enter an insulated module. There, heat recovered from the electrical generator, gas compressors, and electronic equipment is used to melt them. The liquid water is filtered, electrolyzed, and separated into hydrogen and oxygen, just as it was in the previous chapter. The ice extraction area therefore does not operate independently. It depends on waste heat from the other sections, while the atmospheric collection area relies on electricity from the power system. If one section stops working, the balance of heat and material across the entire facility changes with it. The third area lies near an imaginary hydrocarbon lake. A pipeline is lowered into the dark liquid, but it does not simply draw in everything that passes through it. The intake contains a filter screen, temperature sensors, and instruments that perform an initial analysis of the composition. The liquid is brought up in small amounts to avoid overwhelming the system. The mixture from the lake may contain methane, ethane, dissolved nitrogen, and heavier compounds. Some of it is retained as fuel once it reaches the required level of purity. The rest passes through further separation stages to become chemical feedstock. Fuel used by certain machines may tolerate a small amount of impurities if the engine is designed accordingly. But materials intended for plastics, adhesives, or mechanical components require far more precise compositions. A slight difference in molecular proportions could make the final product brittle, excessively soft, or unable to withstand the required temperatures. Here, the distinction between extracting fuel and carrying out industrial production becomes clear. To burn methane, humans would mainly need to control engine efficiency and stability. To manufacture a pipe, a layer of insulation, or a synthetic gear, the chemical composition would have to remain within much tighter limits. The organic dunes around the equator could provide another source of raw material. Robots would scoop the dark particles into sealed chambers, then heat or process them to release useful molecules. But the composition of the dune particles is still not fully understood. A future system may have to test several methods before finding an efficient way to separate them. The purified streams of raw materials finally come together in the manufacturing area. This is not a vast factory with hundreds of production lines. There are only a few small reaction chambers, a forming system, and a three-dimensional printer inside a heated compartment. Carbon, hydrogen, oxygen, and nitrogen are introduced in different proportions depending on the product being made. Some compounds could become plastics used for protective housings, storage containers, or components that do not carry heavy loads. Flexible materials could serve as seals, coatings, or vibration-damping parts. Insulation would help retain heat inside the modules. Adhesives and solvents could support repairs. Simple sections of pipe might be manufactured on site instead of waiting for them to arrive from Earth. A three-dimensional printer could produce a bracket, protective cover, or replacement handle. But it could not print everything from a single material. A component exposed to high pressure requires different properties from an insulating layer. A gear that turns continuously needs a level of hardness and resistance to wear that many plastics cannot provide. Even if Titan offers an abundant source of carbon, the facility would still need precise knowledge of how to transform that carbon into products that remain stable in the cold. Reactions would have to be carefully controlled. Catalysts might need to be brought from Earth, and every batch of material would have to be tested before use. Some ideas go further, suggesting that Titan's resources could support closed biological systems, but that does not mean humans could eat methane or turn organic dune material directly into food. Methane is not something humans can consume, nor could dune particles simply be ground up and carried into a kitchen. A more realistic approach would be to refine sources of carbon, hydrogen, oxygen, and nitrogen into feedstocks for microorganisms, greenhouses, or specially designed synthesis systems. Microorganisms could convert certain simple compounds into useful biological materials. Greenhouses could recycle carbon dioxide, water, and nutrients to grow plants. But these systems would still require light or an alternative energy source, stable temperatures, minerals, and many elements that Titan may not provide easily. A 2026 research preprint emphasized that Titan appears to possess enormous reserves of carbon, hydrogen, oxygen, and nitrogen. These are four light elements essential to fuels, organic materials, and life as humanity understands it. But a self-sufficient facility cannot be built from those four elements alone. Engines require metals. Electrical wiring needs highly conductive materials. Electronics depend on many rare elements. Drill bits, bearings, valves, reactors, and sensors all rely on materials that may not exist in easily accessible quantities on Titan's surface. Models suggest that Titan's rock and heavy metals may lie deep inside, beneath its water ice-rich crust. If this is correct, extracting them would be far more difficult than collecting methane from the atmosphere or obtaining ice near the surface. Outside the modules, the robots continue moving through the darkness. One mechanical arm replaces a filter in the atmospheric collection area. A small vehicle carries ice toward the processing chamber. Near the lake, a pump produces a slow, steady vibration that barely changes. Then another sound appears. The pump begins to vibrate more softly than before. The flow of liquid decreases. The diagnostic system checks the valves, pressure, and pipelines, but finds no blockage. The cause lies deep inside the machine, where a small bearing has been turning continuously through millions of cycles. Its surface is wearing away. The facility can produce plastic to replace a protective cover. It can make a new seal, print a bracket, and clean a pipeline. But the bearing requires a degree of hardness, precision, and resistance to friction that locally produced organic materials may not be able to provide. The sound of the pump gradually slows. Only one spare bearing remains in storage, brought all the way from Earth. Titan may be able to provide gas, water, and carbon, but the small bearing now, coming to a stop, is made from something Titan may not possess. The replacement bearing is installed in the pump, and after several minutes of silence, its slow vibration once again travels through the pipeline system. Liquid begins to move. Methane continues to rise from the dark sea. Water ice is carried into the melting chamber, and the small modules on Titan's surface resume their work. But the recent failure has exposed a much greater limitation. Even if every component remains intact, no machine can operate once the electricity behind it stops flowing. On Titan, energy would not be used merely to power lights or computers. It would have to keep valves from freezing, warm electronic equipment, operate drills, pump gases through pipelines, melt water ice, and split water into hydrogen and oxygen. It would have to maintain the temperature inside the modules, recharge robotic vehicles, and provide enough heat for materials that would otherwise become brittle in the cold to continue functioning. If the power supply failed, the cold of -179 degrees Celsius would not take long to penetrate every part of the facility. So before asking whether Titan contains enough methane or water ice, humanity must answer another question. What source of energy could operate nearly 1.5 billion kilometers from the sun, beneath a thick haze, and for many years without frequent resupply? For robotic missions in the near future, the most reliable option is nuclear power. This is not an entirely new idea. Many spacecraft have used heat released by the natural decay of radioactive material to generate electricity when traveling too far from the sun or operating in places where sunlight is unreliable. Dragonfly, the rotorcraft scheduled to explore Titan, will not depend on large solar panels either. It is designed to use a radioisotope thermoelectric generator commonly known as an MMRTG. Inside this device, plutonium-238 naturally decays and releases heat. Thermoelectric components then convert part of the temperature difference into electricity. An MMRTG does not operate like a nuclear fission reactor. It does not sustain a chain reaction or produce an enormous amount of power. Instead, it supplies a relatively steady flow of electricity over a long period, while also generating heat that can help keep critical systems warm. For a robot operating far from Earth, that stability is more valuable than the ability to produce very high power for a short time. Sunlight on Titan is about 100 times weaker than it is near Earth. The small amount that remains must also pass through a thick layer of organic haze before reaching the surface. A small spacecraft could still generate some electricity from solar panels if they were large enough and conditions were favorable. But Dragonfly requires a more dependable source that does not rely too heavily on day and night, seasonal changes, or variations in the haze above. However, an MMRTG suitable for a scientific probe would not necessarily be powerful enough to operate a resource processing plant, melting many tons of water ice, compressing gases, refining methane, and maintaining a habitable environment for humans would require far more power. A future base might need a fission reactor designed to operate for years or even decades. Such a reactor would generate heat through nuclear fission and then convert that heat into electricity using turbines or another power conversion system. But no specific Titan base design has yet been approved, nor has any reactor been built, launched, and operated on Titan's surface. Such systems would have to be compact enough to fit aboard a rocket, durable enough to survive years of travel through space, and safe enough to operate beside modules containing methane and oxygen. They would also need to inspect and regulate themselves, continuing to function without engineers standing nearby. A large reactor could become the heart of the facility. Its heat could be transferred to the ice-melting chambers, heating systems, and pipelines. Its electricity could run drills, compressors, and electrolysis equipment. With careful design, heat that would normally be discarded could be reused several times before escaping into the environment. On Titan, every unit of heat retained could significantly reduce the amount of new energy that must be generated. Alongside nuclear power, the methane and oxygen produced by the facility could also provide heat or operate engines. When these substances react, chemical energy is released. Some of it could be used in turbines, generators, or heating systems. The rest could be reserved for aircraft, surface vehicles, or rockets leaving Titan. But methane and oxygen are not energy sources that appear from nothing. Methane must be collected and purified. Oxygen must be separated from water through electrolysis, and electrolysis itself requires electricity. When methane and oxygen are burned, they therefore return mainly a portion of the energy that was previously invested in producing them. Chemical fuel can be thought of as a container for energy. When the reactor produces more electricity than the facility immediately needs, the excess power could be used to produce hydrogen, oxygen, or purified methane. These substances would then be stored in tanks. When the base required a brief period of high power, they could be sent into fuel cells or combustion chambers to release that stored energy. This could be useful when a drill starts up, a vehicle needs to take off, or the facility must respond to an emergency. Conventional batteries could play a similar role, but chemical fuels might store more energy for certain tasks. Even so, they would remain a reserve system. The continuous baseline power would have to come from somewhere else. Wind is another possibility. Titan has a dense atmosphere and gravity only a fraction as strong as Earth's. These conditions make flight relatively favorable and also suggest that wind turbines might generate power even when wind speeds are not especially high. A dense atmosphere carries more momentum, so even a slow-moving current of air can exert a significant force on turbine blades. At some altitudes, models suggest that Titan's winds may be much stronger than they are near the surface. A turbine mounted on a tall tower, a balloon carrying a generator, or a hovering aircraft might reach more stable air currents. The energy collected there could then be transmitted back to the base or used to recharge vehicles operating in the atmosphere. But models cannot replace long-term measurements at specific locations. Winds near the surface may remain weak for extended periods. Their direction can change with terrain, seasons, and atmospheric cycles. A turbine placed in an unsuitable location might generate very little electricity. Before building any large system, humanity would need to know the average wind speed, the strongest gusts, and how atmospheric currents change over many Titan years. The turbine itself would also have to survive the cold. Its blades, shaft, and generator would all contain moving parts. Once again, bearings would become a point of weakness. Organic material from the atmosphere could collect on its surfaces. Temperature differences between heated components and those exposed to the environment would cause materials to expand and contract unevenly. Wind might provide energy, but capturing it would require machines far more durable than ordinary turbines on Earth. Titan's methane seas also suggest the possibility of hydropower. Liquids there may move under the influence of tides raised by Saturn, winds, currents between different bodies of liquid, or changes in elevation through narrow channels. If these motions were strong and stable enough, turbines placed within the liquid could convert them into electricity. Kraken Mare contains narrow straits and complex coastlines where currents might become concentrated. Some models imagine small turbines placed beneath the surface or floating devices that follow the flow. Unlike water, Methane and ethane have different densities, viscosities, and thermal properties, so every design would have to be adapted to this unusual environment. However, hydropower on Titan remains a distant possibility. Humanity has not yet gathered sufficiently detailed measurements of the currents, tides, waves, and changing liquid levels within its hydrocarbon seas. A turbine operating in liquid methane would also need to resist leaks, deposits, and material embrittlement. Transporting equipment into the middle of a sea far from the base and maintaining it for many years would add even greater complexity. Solar power is the most familiar option, but on Titan it faces clear limitations. The immense distance from the sun greatly reduces the available light, while the haze scatters and absorbs an additional portion. Seasons lasting many years cause the angle of illumination to change slowly but dramatically, and a day nearly 16 Earth days long means the system must endure extended periods of darkness. Very large solar arrays could still generate electricity. They might be placed at elevated locations, spread across the surface, or combined with energy storage systems. Diffuse light within the atmosphere may arrive from many directions, partly reducing the need for the panels to remain pointed directly at the sunday. But the required surface area would be enormous compared with the amount of power produced. Organic particles falling from the atmosphere could accumulate on the panels. Robots would need to sweep or vibrate the surfaces regularly to preserve their efficiency. The arrays would also have to withstand material contraction and expansion, prolonged darkness, and the risk of damage across a wide area. Solar power could therefore serve as a supplementary source in certain locations, but it would be difficult to rely on it alone for a facility requiring stable power. No single energy source can solve every problem. A practical base might use nuclear power as its primary source because it depends relatively little on weather or sunlight. Batteries and chemical fuels could store energy for periods of high demand or temporary shutdowns of the main system. Wind could provide additional power in favorable locations. Sunlight or the movement of the hydrocarbon seas might contribute a smaller share if actual conditions allowed. Just as important would be the heat recovery system. Heat from the reactor could melt ice. Heat from compressors could be directed toward the electrolysis area. Warm air leaving one module could preheat the incoming gas stream. Water from one process could be retained to transfer heat to the next batch of ice. Instead of allowing energy to escape, the facility would need to keep it circulating within the system for as long as possible. In the model, the small reactor begins operating. At first, only a faint source of heat appears within the core. Then electricity starts flowing through the network. Frost-covered pipes gradually warm. Frozen valves begin to move. Water inside the processing chamber returns to its liquid state, and the electrolysis system once again separates it into hydrogen and oxygen. Methane travels from the storage tank toward the combustion chamber. Oxygen enters through another pipeline. The valves open, and for the first time, a small flame appears within Titan's system. It does not burn in the open atmosphere. It is contained inside a sealed chamber, controlled by sensors, and sustained by the reactor energy that has powered the entire chain of machinery behind it. That flame may be enough to warm a module, recharge a battery pack, or lift a vehicle from the ground. But a crude facility would require far more. It would need to maintain breathable air, water, food, medical support, and stable temperatures for many years, even when one of its systems failed. For the first time, Titan's flame can burn. But a flame powerful enough to keep machines operating may still not be enough to keep humans alive. The small flame inside the combustion chamber is still burning, sealed behind layers of metal and sensors. It warms the pipelines, supplies electricity to a few devices, and keeps the water from freezing again. But beyond the thin walls of the imaginary facility, Titan remains cold, dark, and completely indifferent to whether humans can survive. Machines need only electricity, heat, and functioning parts. Humans require much more. The body must remain within a narrow temperature range. The lungs need a continuous supply of oxygen. Water must be clean. Air must be filtered. Food must be produced or stored for many years. And if part of the human body fails, it cannot simply be removed and replaced with a new component. A person enters the preparation chamber inside the base. A protective suit hangs from a metal frame, connected to air supply lines and a heating system. The outer door remains closed. Only a few centimeters of insulation away lies a dense atmosphere, yet not a single breath of it can sustain human life. Titan has one unexpected advantage over the Moon and Mars. Its surface pressure is about 60% greater than the average pressure at sea level on Earth. A person standing outside the base would therefore not face a near vacuum. The protective suit might not need to remain rigidly inflated against a large pressure difference as it would on the Moon, where the outside environment has almost no atmosphere. This could make certain parts of the suit easier to design. The joints at the wrists, knees, and fingers might remain more flexible if the suit did not need to maintain an internal pressure far higher than the surroundings. Habitats would also not have to resist the full outward force of pressurized air in the way a vessel must when placed in a vacuum. But a dense atmosphere does not mean a breathable one. Titan's air is composed mainly of nitrogen, contains methane, and has almost no free oxygen. If a mask leaked or the air supply system failed, a person would lose the ability to breathe, even though the surrounding pressure remained substantial. The suit would have to provide oxygen, remove carbon dioxide from exhaled air, and filter out unwanted substances. It would also need to prevent liquid methane from touching the skin. Rain on Titan would not simply make clothing wet. Liquid at such an extremely low temperature could rapidly draw heat from the body, freeze materials, and cause severe injury if it passed through the protective layers. The greatest danger would still be the cold. At about -179 degrees Celsius, Titan is far colder than any naturally inhabited environment on Earth. Humans could not endure it simply by wearing a thicker coat. Every part of the suit would have to function as a mobile heating system. Body heat would need to be retained, while moisture and carbon dioxide would still have to be removed. Batteries would have to operate in deep cold. Airlines could not be allowed to freeze. The outer layer would need to withstand impacts with water ice, organic material, and liquid methane without cracking. A heating failure lasting only a few minutes could become an emergency. The cold would threaten more than the human body. Many metals and synthetic materials become more brittle as temperatures fall. Lubricants may thicken or freeze. Displays, wiring, and sensors would need to be kept inside heated compartments. Any device taken outside would require thermal protection, almost like a small room of its own. For this reason, a Titan habitat could not simply be an exposed module resting on the surface. The base might need to be partially buried in the ground, both to reduce temperature fluctuations and to provide additional protection. Organic material or water ice excavated locally could be piled over the roof and walls, adding insulation without requiring all of that mass to be transported from Earth. The modules could be built in several layers. The outermost layer would resist the cold and block methane. Inside it would be an insulating gap, followed by the pressure shell, the network of pipes, and only then the space where people would live. Each entrance might contain several airlock chambers to prevent excessive heat and oxygen loss whenever someone went outside. The living space would probably be far smaller than the imagined cities beneath enormous domes. Every cubic meter kept warm would consume energy. A large but empty room would become a burden. Work, sleeping, and common areas might be placed close together so they could share heat, air, and life support systems. Waste heat from people, computers, reactors, and manufacturing equipment would not be discarded. It would pass through heat exchangers to warm water, incoming air, and pipelines extending outside. On Earth, an overheated room must be cooled. On Titan, nearly every trace of excess heat would have value. Inside the base, the floor might be kept at a comfortable temperature, while only a few layers of material away lies a world cold enough to turn water into bedrock. That contrast would place continuous stress on the walls. A small crack might not cause air to rush out as violently as it would in a vacuum, but it could still allow methane and cold gas to enter, carrying away heat and altering the composition of the internal atmosphere. Titan also has a feature that would make movement feel unusual. Surface gravity is only about 1/7 of Earth's. A person would feel far lighter. Steps could be longer, heavy objects easier to lift, and falls slower. Combined with the dense atmosphere, this low gravity makes Titan especially favorable for flight. Rotors and aircraft wings could generate lift more efficiently, A vehicle like Dragonfly could fly from one location to another instead of crawling slowly across the surface like many rovers on Mars. For humans, this opens the possibility of using small aircraft to travel between facilities, survey lakes, and transport cargo. But the human body was not designed to live for long periods in low gravity. Bones need mechanical stress to maintain their strength. Muscles, the heart, and the circulatory system also adapt to the familiar weight of Earth. In microgravity, astronauts lose bone and muscle mass, even when they exercise regularly. Titan is not a weightless environment, but its gravitational pull is still far weaker than Earth's. No one knows exactly how the human body would change after living there for many years. Nor do we know whether children could develop normally in low gravity, because no generation of humans has ever grown up beyond Earth. A permanent base might need exercise areas with strong resistance, rotating machines that create artificial gravity, or other systems designed to reduce the effects on the body. But every solution would require energy, space, and maintenance. An exercise machine may not seem as important as a reactor, but over many years, it could determine whether the crew remains healthy enough to work and eventually return to Earth. Radiation presents a more complicated picture. Titan's dense atmosphere may shield the surface from many energetic particles more effectively than the Moon, which has almost no natural protection. A base buried beneath local material would gain additional shielding from the soil and ice above. But humans cannot simply appear on Titan. Before reaching the surface, the crew would have to endure a journey lasting many years through interplanetary space. Beyond the protection of Earth's magnetic field, they would be exposed to cosmic radiation and bursts of energetic particles from the sunday. The spacecraft would need shielding, protected shelters, and systems for continuously monitoring their health. Even if Titan's surface is relatively well protected, the total radiation dose accumulated during the journey there and back could still be one of the greatest limitations. Shortening travel time, improving shielding materials, and developing biological methods of protection may be just as important as building the base itself. Time on Titan also moves according to a very different rhythm. A complete day and night cycle lasts nearly 16 Earth days. Light slowly increases, lingers in the orange sky, and then fades over several days. The seasons last more than 7 years, causing climate changes that unfold gradually but may still affect rainfall, winds, and liquid levels in the lakes. Inside the base, humans would probably be unable to live according to Titan's natural day. The biological clock requires a shorter cycle. Artificial lighting would create morning, afternoon, and night according to a schedule chosen by the crew. Outside the window, the sky might remain bright for days, while the people inside pass through several cycles of sleep and wakefulness. The distance from Earth would deepen the sense of isolation. Depending on the positions of the two worlds, a radio signal would take more than an hour to travel in one direction. A question sent to Earth could not receive an immediate answer. Real-time conversations like those possible with astronauts in near-Earth orbit would not exist. If someone were injured, the doctor at the base would have to act before advice from Earth could arrive. If the reactor reported a fault, the engineering team could not wait for mission control to guide them through every step. If food became contaminated or the water system stopped working, decisions would have to be made using only the resources and knowledge already available to the crew. The base would therefore require a very high degree of independence. It would need medical equipment, medications, surgical tools, and diagnostic systems. Crew members would have to be cross-trained so that an engineer could assist with medical care, a doctor could operate basic machinery, and several people could work together during a major emergency. Isolation would also affect mental health. A small group would live within an enclosed space, repeat the same tasks, and see the same faces for many years. They could not leave the base when conflicts arose. There would be no quick flight home. Minor disagreements could persist, while the pressure of work and danger would never completely disappear. The habitat would therefore need to consider lighting, sound, privacy, and the feeling of connection with Earth. A small window looking outside might not be technically necessary, but it could be important for morale. Plants inside a greenhouse would provide more than food and oxygen. They would also bring rare, living color into a world of muted orange-brown tones and frozen darkness. Inside the imaginary base, A person stands behind a multi-layered window. The heating system creates a thin region of warmth around the frame. Outside, droplets of methane begin to fall through the dim light. They strike the ground, gather in narrow channels, and flow toward lower terrain. That person has oxygen to breathe, water to drink, and a reactor keeping the walls from freezing. Perhaps humans could survive here if they brought enough technology, enough backup systems, and the ability to live independently for many years. But surviving on Titan still does not answer the question of why we should travel to such a distant place. The person beside the window continues watching droplets of methane fall outside the base, while another image slowly appears on the screen behind them. It is a map of the outer solar system, where enormous orbits stretch around the sun like nearly endless circles. At the center of the map is Saturn, surrounded by its bright rings and dozens of moons. Titan is only a small point within that system, but if humans could produce fuel, oxygen, and some materials there, that distant point might become an important stop along journeys lasting many years. Titan's value lies not only in the moon itself, but also in its position within the Saturn system. Saturn is not an isolated world. It is surrounded by a collection of icy moons, each with its own geological history and scientific questions. Enceladus sends plumes of water vapor and ice particles into space from its south polar region. Rhea, Dione, Tethys, and Iapetus preserve ancient surfaces, fractures, and layers of material altered over billions of years. Saturn's rings are also a dynamic system, where countless particles of ice move along orbits governed by gravity. A spacecraft traveling to Saturn today usually has to carry nearly all of its fuel, equipment, and supplies from Earth. Every kilogram launched requires energy to leave the ground, escape Earth's gravity, and continue into the outer solar system. Once it arrives, the spacecraft can use only what it brought with it or the power systems designed in advance. If a critical component fails, repair options are extremely limited. If the fuel used for orbital adjustments runs out, the mission may end even while the rest of the spacecraft remains operational. A facility on Titan, if one were someday built and operated reliably, could change the way missions around Saturn are designed. Instead of carrying all the fuel required for years of operation from Earth, a spacecraft might bring only enough to reach the Saturn system and receive additional supplies near its destination. Propellant produced from methane and oxygen could be used for orbital adjustments, landings, or departures from nearby moons. Oxygen, water, and nitrogen could replenish life support systems. Some simple components could be manufactured locally instead of being stored aboard the spacecraft from the day of launch. This approach is known as in situ resource utilization, or ISRU. The basic idea is simple. Rather than carrying everything from Earth, a mission uses some of the materials already available at its destination. On the Moon, ISRU is often discussed in connection with extracting polar water ice to produce oxygen and hydrogen. On Mars, carbon dioxide in the atmosphere and water ice could provide raw materials for fuel and life support. On Titan, methane, nitrogen, frozen water, and carbon compounds offer a different collection of resources. A 2026 research preprint suggested that the presence of carbon, hydrogen, oxygen, and nitrogen could allow Titan to provide some of the raw materials needed for long-term operations. If extraction and processing proved successful, the amount of cargo transported entirely from Earth could be reduced. A cargo spacecraft would no longer need to carry every kilogram of water, breathing gas, plastic material, and fuel required for the mission's entire lifetime. But reducing the launch mass from Earth would not eliminate the need for resupply. Titan may provide many light elements, but electronics, metals, catalysts, and nuclear fuel might still have to be delivered. ISRU would not instantly turn a base into an independent world. It would simply change the balance between what must be brought from Earth and what could be produced after arrival. The first role of such a facility might be to support spacecraft operating for long periods throughout the Saturn system. Small orbiters could approach individual moons, gather data, and return to a maintenance point. Robotic landers could receive batteries, fuel, or replacement components before beginning new missions. A storage facility on Titan could preserve water, compressed gases, and other supplies for long periods. ready for missions that had not even been launched when the original base was built. Enceladus offers a clear example of a destination that could benefit from such a network. This small moon releases plumes of material into space, allowing spacecraft to collect samples without necessarily drilling through its thick, icy crust. A mission could pass through the plumes repeatedly, gather ice particles, and then return to the Saturn region to transmit data, receive maintenance, or refuel. Titan is not located close to Enceladus, but on the scale of the entire solar system. Both belong to the same planetary system. A logistics station on Titan could also support spacecraft traveling farther outward, toward Uranus or Neptune. These two ice giants lie deeper within the cold and darkness. With present-day technology, journeys to them take many years, while favorable launch opportunities depend on the relative positions of the planets. If a spacecraft were already operating near Saturn, receiving fuel and supplies before continuing outward might allow more flexible kinds of missions. A cargo vehicle could depart from Titan, carrying locally produced propellant, tanks of oxygen, or components assembled within the Saturn system. A scientific probe could stop there to inspect its systems before continuing farther. In the distant future, Titan might even become a place where supplies are stored for journeys that would not return to the inner solar system for decades. But the word "stop" can create an image far simpler than the reality. A spacecraft could not merely pass Titan as a car pulls into a roadside gas station. It would have to alter its trajectory, enter the Saturn system, approach Titan, slow down, and perhaps descend to the surface or meet an orbital fuel depot. Every step would require time and energy. Titan's dense atmosphere offers an advantage during arrival. Instead of relying entirely on engines to slow down, a spacecraft could use atmospheric drag. A heat shield, parachutes, or lifting surfaces could convert some of its speed into heat and gradually reduce its velocity. Huygens used Titan's atmosphere during its descent. Dragonfly is also designed to pass through the dense air before beginning its mission on the surface. The low gravity makes flight within the atmosphere more favorable. Wings or rotors could generate enough lift without moving as quickly as they would on Earth. Dragonfly takes advantage of this combination of dense air and low gravity to fly between multiple locations. Instead of moving only a few meters at a time across rocks and dunes like a rover, it can take off, cross difficult terrain, and land somewhere else. A future facility could use similar vehicles to transport cargo between ice deposits, hydrocarbon lakes, and manufacturing areas. Rotors might lift relatively heavy loads in Titan's environment. Balloons or unmanned aircraft could survey areas far larger than those accessible to surface vehicles. However, the atmosphere would help only during arrival and flight near the surface. To leave Titan, a spacecraft would still need enough thrust to accelerate upward. It would have to carry engines, fuel, and oxidizer. The dense atmosphere would even create additional drag during the first stage of ascent. Titan's low gravity would reduce the requirements compared with Earth, but it would not make launching free. If propellant is produced on the surface, but a spacecraft needs it in orbit, another vehicle must carry that propellant upward. The process would consume part of what had just been produced. Storage tanks, pipelines, and transport vehicles would all add mass to the system. A useful refueling station, then, might not exist entirely on the surface. It could consist of a processing plant on Titan and a storage depot in orbit, supplied by regular flights between the two. When Titan is compared with closer destinations, each place offers different advantages. The Moon is near Earth, so travel times are short and replacement parts are far easier to deliver. Water ice in the polar regions could provide oxygen and hydrogen, but the Moon has almost no atmosphere and only limited sources of easily accessible carbon. It may be a suitable place to test the first technologies before using them much farther away. Mars is farther than the Moon, but still much closer than Titan. It has carbon dioxide in its atmosphere, water ice beneath the surface, and stronger gravity than Titan. Many technologies for producing fuel from carbon dioxide and hydrogen have already been studied for Mars, but its atmosphere is extremely thin, making winged flight and the landing of heavy payloads more difficult. Titan has a dense atmosphere, abundant methane, and a richer supply of carbon compounds. It also has water ice and nitrogen, but Titan is far colder, much farther from Earth, and may lack easily accessible sources of metal. A failed component on Mars would already be a serious problem. On Titan, a replacement shipment might have to cross a large portion of the solar system. For that reason, Titan cannot simply be called better than the Moon or Mars by a single measure. These worlds would not necessarily compete for the same role. The Moon could serve as a testing ground and logistics center near Earth. Mars could become a place where humans learn to live for long periods on another planet. Titan, if technology advances far enough, might serve as a logistics base in the outer solar system. But even that role is not guaranteed. A route from Earth to Uranus would not necessarily benefit from detouring through Titan. If changing course towards Saturn, entering orbit, descending, waiting for propellant production, and launching again required more time and energy than the refueling stop saved, Titan would become a burden rather than an advantage. The value of a refueling station would have to be calculated for each specific journey. How massive is the spacecraft? Where does it need to go? How quickly can propellant be produced? Is the depot located on the surface or in orbit? How much energy is required to land and launch again? How long must the spacecraft wait before continuing? Only if the entire chain provides a real benefit would Titan truly become a logistics hub. Inside the imaginary base, the map of the solar system expands across the screen. One trajectory begins in the inner region, passes Saturn, and then extends toward Uranus. Another continues toward Neptune. Small symbols mark Enceladus, the icy moons, and possible fuel depots that may exist in some uncertain future. On the map, Titan occupies an appealing position. Routes converge there and then continue farther outward, as though the orange moon were a natural harbor in the darkness. But the map does not show the years of waiting, the metal surfaces wearing away, the valves freezing shut, or the components that cannot be manufactured from methane. It reveals only distance. All the real difficulties remain hidden within each thin trajectory glowing across the screen. The flight paths on the screen gradually fade, leaving Titan alone within the Saturn system. From a distance, the orange moon appears to be an almost complete storehouse of resources. Its atmosphere contains nitrogen and methane. Its seas hold hydrocarbons. Its crust is thought to be rich in frozen water. Its dark dunes preserve organic compounds formed over immense spans of time. But a civilization cannot be built solely from materials that can be burned, melted, or carried through pipelines. Inside the simulated factory, every system is still operating. Methane is being separated from nitrogen. Water ice is drilled from the ground and melted. Oxygen is compressed into storage tanks. A three-dimensional printer produces plastic pipes and simple protective housings. Judging by the readings on the displays, the facility appears capable of supplying many essential materials on its own. But inside the hidden corner of a pump, a bearing is still wearing down. Within the reactor, the fuel rods will not operate forever. Across the control panel, processing chips, temperature sensors, and electrical wiring are all made from materials that Titan may not be able to provide easily. Models of Titan's internal structure suggest that the moon separated into layers as it formed and evolved. Heavier materials tended to sink deeper, while the outer crust became rich in water ice and organic matter. Beneath the ice may lie an ocean of liquid water, with rock and metal-rich regions located farther below. If this picture is approximately correct, most of the metals required for machinery would not lie just beneath the surface. They may be buried so deeply that extracting them would be far more difficult than collecting methane from the atmosphere or cutting into near-surface water ice. It is important to remember that no deep drilling campaign has directly confirmed that every region of Titan's surface is poor in metals. Current conclusions are based mainly on models of its composition, density, and internal structure. There may be places containing unusual mineral deposits, blocks of rock brought upward by geological activity, or material left behind by meteorite impacts. But no available evidence shows that such resources are rich enough, close enough to the surface, or easy enough to extract to support a large industrial system. A base might therefore still need to import iron and steel for load-bearing frames, rotating shafts, and components that must resist wear. Aluminum may be needed for lightweight structures, equipment, housings, and certain heat transfer systems. Metallic titanium, despite sharing its name with this moon, should not be assumed to exist in easily accessible quantities on Titan's surface. It would still have to be refined from suitable ore. Copper is essential for many electrical systems. Other elements are required for electronics, magnets, memory devices, sensors, and processors. Catalysts that make chemical reactions more efficient may also depend on rare metals. Precision components such as bearings, valves, injectors, compressors, and electric motors require materials with very specific properties that cannot be replaced by just any plastic or carbon compound. A three-dimensional printer may be able to produce a broken cover, a support bracket, or a pipe that does not carry high pressure, but it cannot create a new microprocessor from methane. It cannot print a high-performance magnet without the necessary elements. Nor can it replace a reactor once its nuclear fuel has been exhausted. Nuclear fuel presents an especially clear limitation. The plutonium-238 used in radioisotope thermoelectric generators cannot simply be produced from carbon, hydrogen, oxygen, and nitrogen. A fission reactor also requires carefully manufactured fuel and radiation-resistant materials. If Titan cannot provide those resources, every source of continuous baseline power would still depend on shipments from elsewhere. This does not make in situ resource utilization meaningless. A base does not need to manufacture everything in order to be valuable. If Titan can provide water, oxygen, methane, buffer gases, and some construction materials, the amount of cargo transported from Earth could still be reduced significantly. But complete self-sufficiency is a different goal, and a far more difficult one. Distance makes every shortage more serious. With current technology, a journey to the Saturn system usually takes many years. Cassini required nearly 7 years to arrive. Future missions may travel faster or follow different trajectories, but Saturn will remain extremely far from Earth. If a sensor fails today, its replacement cannot arrive the following week. If the reactor develops a serious fault, no repair crew from Earth can reach the base within a few months. Every system would have to continue operating across periods longer than the expected service life of many ordinary industrial machines. This changes the way equipment must be designed. A factory on Earth can shut down while technicians dismantle an entire pump, inspect each component, and order a replacement part. A factory on Titan would have to detect wear before complete failure, switch to a backup module, and allow robots to replace the damaged component. Those robots would need more than the ability to move. They would have to inspect pipelines, detect leaks, measure motor vibration, and diagnose the cause of declining performance. A robotic arm would need to loosen bolts, remove a module from its mounting, and install a replacement under conditions of extreme cold. Tasks that are simple for human hands could become extremely difficult for robots. A connector may be covered in organic material, a bolt may contract in the cold, a seal may cling tightly to a surface, a camera may be obscured by haze, a replacement component may sit behind another pipeline that the robot was never designed to reach. The machinery would also have to withstand methane, ethane, and organic compounds over long periods. A material that does not react immediately may still change after thousands of thermal cycles. Liquid could seep into narrow gaps and then create stress as temperatures shift. Organic particles could settle on sensors, distort measurements, or cover heat-radiating surfaces. Reliability, then, cannot come only from making each machine exceptionally strong. The facility would also need to isolate failures. If one pipeline breaks, the rest of the system must continue operating. If one electrolysis unit stops, a second module must take over its load. If a repair robot can no longer move, another robot must be able to replace it. That redundancy would increase the mass, cost, and quantity of supplies that must be transported from Earth. But without backups, a minor failure could bring the entire base to a halt. Beyond these engineering limits lies another question, quieter but no less important. Titan is not merely a place filled with resources. It is also a natural laboratory for organic chemistry and for processes that may have occurred before life emerged on Earth. In Titan's atmosphere, methane and nitrogen are continuously broken apart and recombined into more complex molecules. Organic particles settle onto the surface, mix with water ice, and may undergo further reactions when they encounter suitable conditions. Some regions may have contained liquid water in the past because of impacts or geological activity, creating environments where organic chemistry could advance through many additional stages. These processes are not evidence of life. An organic compound is simply a molecule containing carbon arranged in a particular structure. It can form without the involvement of living organisms. Even when an environment provides suitable conditions for prebiotic chemistry, that does not mean biology ever truly emerged there. This distinction is extremely important. Titan may help humanity study the chemical steps that lead toward life, but no data have confirmed that life exists on its surface or within its subsurface ocean. Every discovery would have to be examined carefully to distinguish natural signals from contamination carried by spacecraft. A large industrial complex would make that task more difficult. Exhaust, lubricants, plastics, microorganisms brought by humans, and chemical reactions inside the factory could all spread into the environment. An unfamiliar molecule discovered after years of resource extraction might have come from Titan, but it could just as easily have escaped from a leaking pipe or originated in material transported from Earth. If the scientific goal is to understand Titan before it is altered, large-scale extraction would have to be strictly controlled. Some regions might need to remain completely protected. Industrial facilities would have to be placed far from sites of high scientific value. Robots would need to be cleaned and monitored to reduce the risk of carrying material from one location to another. This creates an unavoidable tension. The regions richest in resources may also be the places scientists most want to study. A hydrocarbon-rich shoreline may preserve evidence of ancient climate cycles. A layer of organic sediment may contain a chemical record stretching back millions of years. Extracting it too soon could destroy the very information humanity traveled so far to understand. The 2026 research preprint proposed many intriguing possibilities for using Titan's resources, but it remains a work of synthesis and proposal, not proof that a real factory has been demonstrated to be technically or economically viable. No production line has ever extracted methane on Titan. No electrolysis system has operated for years upon its icy surface. No robot has autonomously replaced hundreds of components at -179 degrees Celsius. And no complete calculation has yet shown that the total costs of launch, construction, operation, and maintenance would be lower than the benefits gained. These ideas may be chemically reasonable and still fail because of their energy demands. They may be technically possible but far too expensive. They may work on a small scale without expanding into a major logistics facility. Or they may benefit certain routes while offering little value for others. Inside the simulated factory, the systems begin to reduce their output. The drill comes to a stop. The flow of methane through the pipelines gradually slows. The electrolysis chamber completes its final batch and closes its valves. Robots return every tool that can still be used to storage. There is no explosion, no cracking wall, and no catastrophic failure. The facility simply stops before a long list of unanswered questions. How pure is the ice? What do the organic dunes truly contain? How long can the machinery continue operating? Where are the metals? How would nuclear energy be supplied? And how could humanity extract resources from a world without destroying its scientific value? Titan may contain nearly every light element a base would require. But civilization is not built from air, water, and carbon alone. It is also built from small, precise components that are difficult to replace. The final door of the simulated factory closes. Outside, the orange haze continues settling slowly over the dark dunes, while the methane seas remain still beneath the frozen sky. Before humanity can build a refueling station, a much smaller machine will first have to discover what Titan's ground is truly made of. The final door of the simulated factory has closed. The pipelines no longer vibrate. The drill rests motionless on the dark ground, and the storage tanks hold only small amounts of methane and oxygen produced within our imagination. Our imaginary spacecraft begins to rise. Below, Titan remains unchanged. Organic dunes stretch beneath the orange haze. The northern seas remain dark, and water is still locked within an icy crust colder than any winter on Earth. Our journey has carried us through a vision of the distant future. We have imagined drills extracting ice, factories separating methane, reactors supplying heat, and spacecraft stopping to receive fuel. But today, No base or resource processing plant is being built on Titan. The real machine being prepared for this world is much smaller, and its first task is not to produce fuel, it is to take measurements. That machine is called Dragonfly. It is an autonomous rotorcraft about the size of a car, using 8 rotor assemblies to take off, fly across the terrain, and land at multiple locations. Titan's dense atmosphere and low gravity allow an aircraft to move more easily than a rover forced to crawl across dunes and poorly understood terrain. Dragonfly will be like a laboratory capable of carrying itself from one place to another. According to NASA's schedule as of July 2026, Dragonfly is moving toward a launch in July 2028. After a journey lasting about 6.5 years, it is expected to reach Titan in December 2034. These dates may still change as construction, integration, and testing continue, but the mission remains in development according to that timeline. When it arrives, Dragonfly will have to complete an autonomous descent through Titan's dense atmosphere. A heat shield, parachutes, and flight systems will operate in sequence before the rotorcraft is released to stabilize itself and approach the ground. Because radio signals take more than an hour to travel from Titan to Earth, no one will be able to control each movement in real time. The machine must determine its own altitude, winds, and surrounding terrain, then guide itself toward a safe landing beneath the orange sky. Dragonfly will spend most of its time on the ground, taking measurements, analyzing samples, transmitting data, and recharging its systems. Once it has studied one location thoroughly, it can take off and land in a new region. During its primary mission of more than 3 years, it is designed to visit roughly 20 to 30 sites and travel a total distance of nearly 115 kilometers from its initial landing point. Dragonfly's electricity will not come from large solar panels, because sunlight at Titan is extremely weak and must also pass through the organic haze. The spacecraft will use an MMRTG, a device that converts part of the heat released by the natural decay of plutonium-238 into electricity. This heat will also help protect critical systems from the extreme cold, allowing the robot to operate for long periods without depending on weather or the day and night cycle. Dragonfly will not travel directly to the methane seas near the North Pole. Its initial area of operation lies near the organic dunes around the equator, where Cassini observed long, dark bands. The material there is thought to have formed in the atmosphere and settled onto the surface over immense spans of time. The exact composition of these dune particles remains an important question that Dragonfly will investigate directly. The spacecraft carries instruments designed to study the chemical composition of the surface and the shallow material beneath it. A drilling system can collect material and transfer the samples to analytical instruments. Dragonfly will come into direct contact with organic particles, water ice, and mixtures on the ground, revealing which molecules are present, how complex they are, and how far carbon chemistry has progressed on Titan. Another major objective is to find places where carbon-rich material once came into contact with liquid water. Titan's surface is now too cold for water to flow freely, but in the past, a large impact may have melted part of the icy crust for long enough to allow water to mix with organic compounds. These temporary environments may have acted as natural laboratories where chemical reactions associated with the stages before life had an opportunity to occur. Dragonfly will also study geology and weather, measuring temperature, pressure, winds, seismic activity, and changes around each landing site. Its cameras will record the shapes of dunes, pieces of water ice, and surface structures. Each flight will not only carry the spacecraft to a new location, but also help connect its measurements on the ground with the broader picture left behind by Cassini. Dragonfly's objectives are often described as the study of habitability and prebiotic chemistry. Habitability does not mean that a place definitely contains living organisms. It simply asks whether the environment has ever offered conditions that life as we know it could use. Prebiotic chemistry examines the transformations of matter that occur before a truly living system emerges. Dragonfly should therefore not be understood as a machine that will land and provide a simple answer to whether Titan has life. The mission is not designed to prove the existence of living organisms through a single measurement. It will investigate habitability, prebiotic chemistry, and possibly identify noteworthy chemical signatures. Any unusual molecule would still have to be examined to determine whether it could have formed through non-biological processes. NASA also describes Dragonfly as a mission studying the chemistry that precedes biology, rather than one designed to detect life directly. That is why Dragonfly matters to the dream of using Titan's resources, even though it carries no equipment for building a factory. Before drilling ice on a large scale, humanity needs to know how hard, pure, and uniform the near-surface material truly is. Before turning organic dunes into industrial feedstock, we need precise measurements of their composition. And before placing robots there for years of work, we need to understand how dust, wind, temperature, and terrain will affect machinery. Dragonfly will provide only part of the answer. It is not designed to investigate the polar methane seas directly. To determine the depth, currents, and composition of Kraken Mare or Legia Mare, humanity may need a new orbiter, a floating probe, a submarine, or another specialized instrument. The coastlines and northern polar regions will have to wait for a different mission. The water ice crust will also require much closer study. A future base would need to know how deeply the ice is buried, what impurities it contains, and how much energy would be required to extract it. Later missions may have to test drilling, melting, filtering, and electrolyzing water under actual Titan conditions. Only after a small processing system operates reliably could humanity begin to imagine a larger factory. Energy remains the central question. An MMRTG is suitable for Dragonfly, but it would not be powerful enough for a large production facility. Humans would have to develop reactors that could be launched safely, operate for decades, and regulate themselves without engineers nearby. Robotics would also have to advance far beyond present capabilities. A factory would need machines capable of replacing pumps, cleaning pipelines, inspecting cracks, and responding to failures that had never been predicted, all within the extreme cold and among methane, ethane, and organic material. If humans ever travel to Titan themselves, other questions will emerge. The long-term effects of living in gravity only about 1/7 as strong as Earth's remain unknown. A crew would also need faster transportation to Saturn, better radiation shielding, and a reliable way to return home if the base suffered a serious failure. Titan itself would also need protection. Before extracting material from its dunes, ice, or hydrocarbon seas, humanity would have to identify regions that should remain untouched for scientific study. Robots and equipment would need to minimize the transfer of microorganisms and chemicals from Earth into natural samples. A world of such great scientific value cannot be turned into an industrial zone before we understand what might be altered. In the end, every idea must survive a practical calculation of costs and benefits. A factory might work chemically yet consume too much energy, produce materials too slowly, or depend on too many imported metals and supplies of nuclear fuel. Only if the entire chain of extraction, processing, maintenance, storage, and transportation provides a genuine advantage could Titan become a true logistics hub. Our imaginary spacecraft is now rising through the orange haze. The factory modules shrink into tiny points below, then disappear completely. Beneath them, the methane seas remain dark. Organic dunes continue to stretch around the equator. Water remains locked within the icy crust, holding oxygen and hydrogen inside bonds that have not yet been broken. No city lights appear. No rocket is waiting to be refueled. There is only a world containing materials that human civilization already knows how to name, but does not yet know how to use at such a distance. Titan is not a gas station waiting for humanity to open its doors. It is a reminder that in space, resources are only the beginning. To transform methane into fuel, ice into oxygen, and a distant moon into a place of shelter, humans would have to bring energy, machinery, knowledge, and the ability to live independently for many years. Perhaps one day, a spacecraft returning from the depths of the solar system will descend toward Titan, fill its propellant tanks, and continue on its journey. But before that day arrives, Dragonfly will fly across the frozen dunes, listen to the winds moving through the orange atmosphere, and search for the answer to a more modest question. What is Titan truly hiding beneath its haze?